So, good morning. Today we will have our last lecture on random processes, and from next week onwards we will move into actual estimation. So, before ending, I thought that there are some topics left here and there, so we should discuss them little bit. Then we should briefly summarize what we have done, and perhaps try to take a brief look on what we are going to do. So, these three things came into my mind because many times we will be talking about them, and there are certain facts which we should know before we close our discussion on random processes. The first thing that is I thought we should discuss the normal distribution. As such, we have not discussed any of the distributions as a case. There are many examples in books. There are various kinds of distributions which are used in various kinds of applications. For example, if you read a book on queuing theory, you will mostly get across the Poisson distribution, the exponential distribution. If you read a book on reliability, you will come across the Weibull distribution. Similarly, if you read a book on signal processing, you would very much come across the normal distribution. That is, so let us take a brief look at the normal distribution. It's a very special candidate which is very often quoted. So, this is the normal distribution. I think you know it. This is the normal distribution of a single variable, and in fact its values are sometimes tabulated in charts in terms of a normalized normal distribution. That is, a function, this function is the normalized form, and the general, that is, this is the normal distribution with mean mu and variance sigma square. And as you can understand that the whole distribution itself is given in terms of mu and sigma square. So, if mu and sigma square are known, then the whole probability distribution is known. This is one of the biggest advantages of the normal distribution, that the whole probability density function is characterized in terms of what is known as first and second order moments. In general, for a probability distribution is a much more detailed information rather than the first and second order moment, but in the case of this distribution, if you know the mean and the standard deviation, then you know the whole distribution. So, it only that much needs to be known. That is one advantage. This function is sometimes called error function. This function is also in many cases tabulated. That is, this minus in this is, you will find that there are various statistical charts in which this function and this function are, generally this function is tabulated. So, if you are given any other mean, you have to first transform that your distribution to this distribution, and then if you want to get the value, because this is a very odd integral, it is not easy to get the value directly analytically. So, this is sometimes tabulated, and obviously though it looks like this, it can be verified that this is itself this is indeed a distribution function, and minus infinity to plus infinity x is 1. In fact, to make it 1, this factor has been added, otherwise this integral itself will not give 1. So, just to make it 1, this factor is added. So, this is the normal distribution which is somewhat known, but we in general are talking about, we will be dealing with various quantities. So, we have to first understand what is a jointly normal distribution. So, jointly normal distribution is, one thing I did not draw is that the normal distribution curve So, the normal distribution is in general a bell shaped curve whose so that bell peak happens at mu. Maybe this is the origin of the axis. It is not always necessary that it will be at 0. So, maybe this is 0, and the sigma is such that there is in the sometimes I do not know, sometimes in those of you who are familiar with management sometimes might have heard of the term called 6 sigma. It is a quality control practice, and that name 6 sigma is basically derived from the normal distribution. Okay. So, if you see the normal distribution, then if you take plus minus 6 sigma, suppose the normal distribution has a standard deviation of sigma, then 99.3% of the area falls within plus minus 3 sigma. This side is 3 sigma, this side is 3 sigma. So, this is plus 3 sigma, this is minus 3 sigma. If you take this limit, then 99%, then the area under this becomes 9.9935 or something. So, 99, and the whole area is from minus infinity to plus infinity is 1. So, 99% of the area falls within that band, right. That is why in many engineering applications, when we describe variations of parameters, then we often say that this is a plus minus 3 sigma limit. That is, the parameter variation is in general random. In all engineering designs, there are some parameter variations which occur, and you have to take care of such variations in your design. So it is common practice to characterize that your design has been verified under what parameter variation. So, sometimes people say that it is verified under plus minus 3 sigma variations. Now in management they are saying that you should have such practices such that plus minus 6 sigma of your produced products will actually meet quality. There will be no all products. So, if you take plus minus 6 sigma, then this becomes some 99.99999%. So, when they say in management that some companies 6 sigma has now become a quality standard. So, if some company 6 sigma compatible, then they are trying to make a claim that their products, that so many of their products meet the stated quality, right. So, that name in management also derives its origin from the normal distribution. So, if in one dimension it is this curve, then in 2 dimensions it is going to be like a dome which is circular in cross section, right. So, I have tried to draw that. So, if you have two random variables which are supposed to be jointly normal, then you get a form like this, and the shape looks like this, where this is the mean. So, on the x axis you have a mean mu1, on the y axis you have a mean mu2, and that is characterized. So, you see that it is similar, only mu1 mu2 sigma 1 square sigma 2 square, but there is a correlation coefficient. So, 2 random variables may be correlated to a certain degree, and in general they may be jointly normal and correlated. And it turns out that if you take these are what? These are called the marginal densities, if you recall. So, from this you can get only the variation, the probability density of x by integration getting with respect to y, remember. So, if you do that, then the individual ones become Gaussian densities. So, both this and this are Gaussian individually, and they are jointly Gaussian too, right. And you can also verify that if r is equal to 0, which means that they are uncorrelated, then they also become independent, because if r is equal to 0, then this term will vanish then it becomes e to the power this, all these will become 1, and this term will become simply e to the power minus this plus this, which means that fxy equal to fx into fy. So then they will become independent also. So if they are uncorrelated, they are independent. This is a direct consequence of the fact that the distribution function is fully characterized by the second order moment. So if the second order moment satisfies the uncorrelated property, then the whole distribution becomes independent, which is not the case for general distributions. Now, what is so great about this distribution? I mean, why is it so common? That is because, you know, what are we going to do? As you will see that we will in most of signal processing and estimation theory, people generally work with linear models. That is because it's simpler. Otherwise, you know, on one side you have this probabilistic uncertainty and random things. Now, if you put nonlinear systems into that, then it will blow up. I mean, it's very difficult to get results. So people first try to see that how, let us have some randomness, and then try to see how it transforms through linear systems. So people largely use linear models and try to get results, and you can get, I mean, in many applications you can get reasonably good results. Things are used, and right. Now it turns out, so what are we going to, if the moment we use linear models, what kind of computation are we going to do? We are going to basically multiply things by constants and add. So we are going to do linear operations. So all variables will be going through one after the other various kinds of linear transformations when we are using a linear model in our computation. Now the point is that will mean that the probability distributions of the input variables will continuously get changed. So one of the biggest advantages of the Gaussian variable is that they maintain their Gaussianness with respect to linear operations. This is one of the biggest reasons why we always tend to assume Gaussian variables when we talk, especially when we discuss signal processing. Almost, I mean, some people think that white noise cannot be anything other than Gaussian. I mean, Gaussian white noise becomes a term. Actually, there is no relationship between noise being white and its PDF being Gaussian. They are actually two different things. They are quite unrelated. But sometimes, I mean, we get so much use that we always think that, I mean, if we have a noise, it must be Gaussian. It becomes so common, I mean, sometimes in books, etc. So these are some of the properties which are useful. So first thing is the simple version of it, which says that if x and y are jointly normal, then you make any linear transformation variable z by ax plus by, and you take another linear transformation w, which is cx plus dy. Then z and w are also going to be jointly normal. So once you have assumed one to be normal, even if you do linear arbitrary linear operations on them, they also remain normal. So they remain normal means they are still also characterizable in terms of their means and standard deviations. So whatever operation you do linearly, all you need to characterize to get full information is mean and standard deviation. You only need to know how these are transformed during your linear signal processing, nothing else. That's a big advantage. I mean, that's why you will see that we always try to characterize these things, and if we have assumed Gaussian, then we are sure that if we can characterize these two things, we have characterized everything. That is the advantage. There are also other facts. For example, it turns out that a large number of real random variables do tend to approximate the Gaussian curve reasonably. There are a large number of random variables which occur practically, which will tend to approximate. I mean, they are if you actually carry out an experiment and plot a histogram, you know, I mean, how do you plot this probability density function in practice? You have to do a large number of experiments, and then you have to plot what is known as histograms. I think we learned that in school, that we will characterize that, okay, how many boys are there within this group x1 to x2, and then how many boys are there within x2 to x3, and then we'll plot them histogram. So if we take a large range and if we take small ranges, then it will try to approximate this. I mean, that's how we draw the probability density function. So that is also another reason that it actually occurs in practice in a large number of cases. So people are happy that it's a practical distribution which has nice properties. That's why people use it in this application. In other kinds of applications, people will use other distributions, but in our application, Gaussian will be useful. Similarly, if x and y are jointly normal, then the conditional density of y given x also happens to be normal. Okay, so in many cases we will see this is a very common thing that we will do, because we are in many cases we are in general about uncertain things. What are we interested in knowing? Our whole course is about estimation, and from the next class onward we will try to see that how we can get a good guess about something in the face of randomness. That is the whole that is what the whole course is about. And one of the main things that you would like to know is what is expected. That is, in some probabilistic sense, what is the average. So the expected value in general is of great interest in this course, and obviously we are not trying to find the expected value in absence of any information. So we in general will try to get as much prior information as possible, and then try to find out what is expected. Is it not? Because we are always trying to make guesses in certain specific cases. So we will always try to incorporate the information about those cases, whether the signal is what kind of signal we are applying. Suppose we are trying to find out what is going to be the output. So obviously we will try to incorporate information about what is going to be the input, or right. So we are not in general only interested in probability densities. We are in many cases interested in conditional probability densities, because we already have some facts available. So we will try to incorporate them in our estimate. Okay, that's what the conditional estimate does. It does not get y for arbitrary values of x, but it finds out that value of x which has occurred, probably something else, and then from there tries to guess what is the expected value of y. That's why it is so important. So it turns out that this conditional estimate also happens to be normal. So again, you only need to characterize covariance and mean. See, this is the central reason why in signal processing people will always tend to use a Gaussian noise. And in general if you have this result that if there are n random variables, and if you make any arbitrary linear combination of these random variables, a1 x1 plus a2 x2 plus a3 x3, then for arbitrary a1 a2 this variable y is going to be normal, right. So that's a good thing, which means that if you take a vector whose all components are actually random normal variables, then you make any linear transformation of the vector multiplied by any constant matrix, the resulting vector is also going to be jointly normal. And in our linear processing we only do that, we only multiply signals by constant matrices everywhere, right. So we are going to always remain normal. That's such a nice mathematical advantage. So this is one point which I wanted to make, because sometimes people wonder that why is it that I am not taking a Weibull distribution of noise, because if we take a Weibull distribution of noise we will quickly get lost after one or two transformation. We won't know what distribution the output will have. That is the problem. Next we talk of white noise. So we will in many cases again assume that the input is white noise, or we want to make something white, we want to make the innovations white. We will get these things in our course very often. So we should know what is white noise. So white noise is something, actually this is stated in terms of okay, you can interpret it in the discrete context also, that a noise is called white if its covariance, this is the covariance. Covariance means expectation of x minus xt minus mu. Let us take a stationary process. So mu constant. So covariance CT1 T2 is what? It is expectation of x T1 minus mu into x T2 minus mu. This is auto covariance. You can have cross covariance also, okay, in general. So what does it say? What is this delta function? In case of continuous, this delta is the what is known as the Dirac delta. There are two kinds of deltas. One kind is called the Dirac's delta, another is called the Kroneker's delta. The Kroneker's delta is the discrete delta function, which says that for the Kroneker's delta, delta tau is equal to 1 for tau is equal to 0 and is equal to 0 elsewhere. So it is plotted, it looks like a function like this. Its value is 1. In the case of Dirac delta, its value is infinite, but the integral under it is 1. It has it has unit area. So what does it basically say? So whether it is continuous or discrete, it basically says that that the two values of the random, if you take two different random variables which are even a small time apart, they are going to be uncorrelated, because this value will be 0. If T1 minus T2 equal to 0, only then this has a value. If T2 is any different from T1, then this delta function is going to be 0, because it is 0 everywhere else other than at 0. So which means that this covariance function is going to be 0 for all T1 T2 such that T1 is not equal to T2. It is non-zero only when you calculate C T1 T1, otherwise you take any other T2, it will be 0. So all random variables, so if you take a random signal, I mean, which is occurring, that is one instant of the random process, then if you take the random variable at any T1 and if you take a random variable at any T2, then these two random variables are going to be uncorrelated, and this will happen for arbitrary T1 T2. Right? That means that things are really random. I mean, there is you cannot extract any information. If you get property of, let's say if you measure any one of them, you cannot say anything about the other one, because they are totally uncorrelated. See, correlation generally lets you guess what is going. Suppose two variables are positively correlated, then on an average, if one is positive, then the other is also positive. So you can at least make some guess about it. But uncorrelated means that the individual random variables at the various times are completely uncorrelated. For example, what is going to happen 2 minutes later, even if you have data up till on that thing, even if you have data about the behavior of an object for the last 10 years, you cannot say what it is going to do in the next 2 seconds, because this whole behavior over the last 10 years, every point of it is actually uncorrelated with the next 2 seconds. So everything is uncorrelated. So it's an ideally random process. In that sense, it is ideal. You cannot extract any information about anything from any other point. Each one is independent, right? So it's, in a sense, it is the peak of randomness. Okay, as far as second order moments are concerned. And why is it called white? Because in general, when we say white light, I mean, that's how the name has come. White light means it contains all spectrum of the VGR, right? So, and spectra are actually related with frequency, because color comes from frequency. So it means that it contains all frequencies. Why it contains all frequencies? That comes from this integral. So now if you see the power spectrum of power spectrum is actually defined like this, right? This should be minus infinity to plus infinity. Now, if this r tau is this, so only at tau equal to 0 this is going to have, this is going to be non-zero. At every other point it is going to be 0, this is going to be 0. So, this integral value is always q, actually q 0. Right, which means that irrespective of omega, so now see S is actually should be a function of omega, but it is not a function of omega, it is a constant, which means that at all omega S omega is q, which means that power is uniformly distributed over all frequencies omega. So, there is equal power in each frequency, that is why it is, I mean there is a, people try to draw a similarity between white noise and white light, because white light also contains all frequencies, that is how the name has come, right. And I mean there are various, because of this nice property of the, because of this nice nature. So, you see that we have to remember that the power spectral density of white light is like this, of white noise is like this, while its autocorrelation function is like this. Okay. So, so this we should remember, because this we are going to use in many cases. This is but one thing I would like to mention again, that this you must remember, that again that white noise has no relationship with Gaussian. You can have you can easily have uniform white noise. There is no problem about it. Actually, let us, if you see what does whiteness talk about? If you have a random process, whiteness comes from the property of the behavior of one random variable at any given instant of time t1 and another random variable at another given instant of time t2. So, whiteness tries to characterize the joint properties of two random variables at two different instants of time. In fact, because it is stated in terms of the correlation function, white, the signal is called white if it has a certain correlation function. So, whiteness merely says that correlation function is of a certain type. It says nothing about what is the probability distribution of these individual variables. When we say Gaussian, we are saying that if we generate several such random processes and take for each one of them, if we fix the time t1, remember that if you in general a random process is a function of two things, t and xi. If you freeze xi, you get a function xt. If you freeze t, you get a random variable xi at t, right. So, when we are saying Gaussian refers to a random variable. It is a density function, so it must refer to a variable. So, when we are saying Gaussian, we are talking about random variables at a given time, So, if we make many such random processes and at every time sample at 1 second and take the value, and then if we plot those values, then we will get a Gaussian probability density function. That is what we mean. But that statement says nothing about how these variables are going to behave. If you take two random variables at time t1 and t2, what is going to be their joint behavior? That is not stated in the word Gaussian. Gaussian is concerned about a one time, while whiteness is essentially concerned about two different times, or in general n different times. So, they are two different things. We only assume Gaussian and white for analytical simplicity, but it's in no way implied that all white noise needs to be Gaussian. So, this is another point that I wanted to make. Finally, you will sometimes again assume that things are ergodic. Now, what is ergodic means? You know, one of the big problems of especially when we will do signal estimation, we will in many cases we have to try to compute statistical quantities, and we will try to do things in a statistically optimal way. Now, point is that doing things in statistically optimal ways means that we will have to extract statistical information, things like what is expectation and etc. Now, the point is that how can we get expectation? Well, I mean, how can we evaluate expectation when we are doing something, let us say, in real time? Because if you want to do expectation, essentially you will have to carry out many experiments, because expectation, all the averages that we have talked about till now are all ensemble average sometimes, right. So, ensemble average means that you are supposed to carry out a large number of experiments, get a large number of outcomes, and then average over them, right. Now, the point is, it is very inconvenient to do an ensemble average when you are doing something in real time. I mean, you are already in the middle of doing something. How can you do an experiment? You cannot do an experiment. So but you have to try to get an idea of statistical quantities based on what you have. Now when you are doing an experiment, what do you have? You have functions of time. So you have spent time from you are actually doing. So you already have past values of a signal. So you have one particular signal at various time instants you have. In general, this is the situation, but in general you cannot do n experiments. So the question is that, so people ask that whether it is possible that if we do some operation based on these time signals, then also we will get the statistical thing, right. For example, can I get the mean? See, the mean of a signal is its ensemble average. You have to do n experiments, see values, then add up. But what they are saying is that, can I calculate a time average and then expect that the time average will somehow be equal to the ensemble average? Remember that if this is a random variable, this is also a random variable, naturally, integral of a random variable over finite time. Now, the question is that, can I expect that this will be the mean of this? So, I am not doing ensemble average, I merely have time values of the random process at various times. Can I expect that this will be the mean? Now, firstly, you will recall that this thing applies only for stationary processes, because if this mean, in general, this mean is a function of time. In general, for general random processes, expectation of xt will be mu t. It depends on at what t you are doing it. So obviously, if you do time average and if it is a function of time, this will never match, because the time average does not have a time argument at all. It is a constant number. So this discussion applies only to the case where the mean is a constant. That means to stationary processes. Okay. So now question is that, when even for those, when can you say that this will be the mean? So that, first of all, let us note that, suppose this I am saying that it is an estimator of the mean. After all, I am doing some computation based on some random variables and then trying to say that is it the mean. I mean I am trying to kind of estimate the mean through this. So this integral can itself be thought of as an estimator. Remember that in the last class we were doing that if you take a random variable x1, x2, x3, xn, and then take all of them and then sum and then divide by n, then it becomes some mu n. We were doing that problem. So that mu n is nothing but an estimator of mu. So here also this is an estimator of mu. Now the question is, what are the properties of this estimator? Is this estimator good? So the first property is that expectation of eta t, that is, if you take an ensemble average of this, it will be the mean. Why? Very simple, because if you take expectation of this, you will put expectation of this, and this expectation will now move here, move inside the integral, and then it can be replaced by mu. So it will be minus t to t mu dt 1 by 2t, which is mu. So at least the expectation of this estimator is the true value. So it is, in that sense, it is an unbiased estimator. But what is the use of the estimator being, what is the use of the expectation being equal to the mean? In a given case, will it be close? That is what we are interested, right? So for that you have to know whether this is, as t tends to infinity, whether the standard deviation also becomes 0. Remember we were saying, remember that if we have x1, x2, xn, then as we increase n, standard deviation becomes sigma square by n. We had done in the last class. So there, as n you increase, that sum is nothing but this integral in the discrete case. So there we were finding that as if you increase this capital T, that is do the integration over large and large intervals, then you will get your time average will tend to match the ensemble average more and more closely, in the sense that if you do a particular signal and then do it, you may be away, but you are not likely to be very much away. The more interval you actually integrate on, the better will be your guess. But there are some kinds of processes where you can actually show that by doing a sufficiently long amount of long integration, you can actually get the real true value. That is, if you do it very long, then every time you will get the mean. So such processes are called mean ergodic processes. Okay. Now one of the advantages of that is that, see, as I said, that why we need to make this assumption sometimes, because we will, when we compute real algorithms, then we will not have ensemble average, and we will still need to generate estimates of the mean of signals. So we will say that we will average them in time, and then under the assumption that the process is ergodic, we will say that this computed mean is close to the distribution mean. We'll make that assumption. That's why it's needed. Yeah.
Ergodic and stationarity is similarity. How they are different?
No, if it is stationary, for being ergodic, it must be stationary, because otherwise, if the mean is a function of time, and then you are averaging over time, then you will definitely not catch this thing. But all stationary processes need not be ergodic.
So standard deviation should be 0 for that.
No, standard deviation will be 0 if standard deviation of this will be 0. Standard deviation of the random variable is not 0. Standard deviation of the estimate, standard deviation of the time average minus the mu x goes to 0 as t tends to infinity. So as you are doing a larger and larger average. So that is all that I wanted to mention, new facts. So now, so we have done some, covered some basic ground on random processes, starting from, I must admit that I have been somewhat fast, but remember that we had started from the bare definition of probability, which is taught in school, and then I didn't expect anything else. So from there we have come here. So we necessarily had to be fast. Anyway, we tried to make up. But this is to some extent, this is necessary to firstly to understand the nature of probability and the nature of some of the results that we are getting and why we are doing it, because now in the course of our discussion we can freely talk about conditional expectations, we can freely talk about Bayes kinds of estimators. So that is why it was needed. And so now in the next part of the course, we still have not covered certain things, like in estimation, in many cases we are concerned about, we have algorithms which are called recursive, right. See, we are what are we what is our central concern in estimation, that is we have certain signals which are coming from processes in estimation, and we want to, based on those signals, we want to compute other quantities. Those quantities can be many things. So, in our setting we generally have a dynamic process, either known or unknown, and we have several signals going in and several signals going out. There are also there may also be internal signals. So, these signals, some of them may be measurable, some of them may be not. So, number one, we will discuss this in more detail. This is just going to be this is just 5-minute introduction. So, what is your situation, that you have a dynamic system, you have certain input signals which may or may not be measurable. Even if they are measurable, they may be measurable with a certain uncertainty. For example, all sensor signals suffer from some amount of uncertainty, and then based on these signals we ask some question about what? Could be about different things. Could be we say that given these signals, can we guess some of these internal signals? That is one problem, which is called state estimation, which we will do in great detail. We can ask that given these signals in the past, can I estimate this signal in the future? Can I say that if I have samples of y from 0, 1, 2, 3 up to capital N, and if I have the samples of u from 0, 1, 2, 3 up to u n plus 2, can I guess what is going to be y n plus 2? See, I am standing at n, so y n plus 2 has not yet occurred. I am trying to say that I have some measurements of the past and some inputs applied and some of the outputs I have measured, and now I am asking that if I apply the input at n as this much and the input at n and at n plus 1 this much, what is going to be my output at n plus 2? This is the question that I am asking. It has not yet occurred. So, it has not yet occurred means that obviously y is not only affected by u, because if it was only affected by u, then there is nothing uncertain about it. And if you know the system, and if you know u, and if you know that y is only affected by u, then you have a deterministic scenario. So, y is not only affected by u, it is affected by some other random quantities, and those you are talking about them in future. So, you do not know what they will be. So, that is the uncertainty. So, in the face of that uncertainty, can you guess what y is going to be? This is a very useful question to ask in many situations. For example, I mean several situations. For example, if you could estimate the stock market tomorrow, you would become a billionaire. If you can hit one aircraft with a missile, that also involves this prediction, because the pilot is maneuvering. See, the pilot is trying to save himself. So, he is sometimes accelerating, sometimes not accelerating, sometimes in the x plane, sometimes in the y plane, sometimes doing s maneuvers, various things. So, you do not know what he is going to do, but you have to still guide your missile. So, can you guess where the plane is going to be over the next 2 samples? This is the question. If you want to do, I don't know whether you have seen, I was very impressed by the National Geographic clip where one scientist showed, I mean they were having a problem with this thing on active noise cancellation. So, active noise cancellation is where you cancel one noise by generating another noise, so that they destructively interfere. See, noise is nothing but sound waves. So, if two waves constructively interfere, then the noise will get increased. If they destructively interfere, then the noise will go. So, the question, and noise is a random thing. So, he was showing that he was creating noise by a machine, and he had put some thermocol type balls on the surface, and because the surface was noisy, so it was vibrating and the balls were jumping, and the intensity of noise you can easily visualize by the amount by which the ball was jumping. So, then he switched on his noise canceller, and immediately the balls, it came to 1/10 of the height, and visibly the noise signal was gone. Now, how is it done? If you want to cancel noise, then you have to estimate what is going to be the noise in the next instant and then generate an anti-noise, right. So, there are very practical applications where such things will be needed. Similarly, another very common question that may be asked is that given this and this, can you guess what is this? This is for those who are in control, this is a fundamental question. All control designs start with a model. If you don't have a model, you can't design a controller, right. But the trouble is that in many cases, when you are trying to design controllers, you don't even have a model, because of the fact, especially for unstable plants, how can you even get this and this? There are some plants which will not even operate unless it has a controller, but for a controller you need a model. So, how do you get a controller without a model? This was a situation which occurred in our, let us say, in our LCA design. You see, LCA is an aircraft which, if it has to fly, it needs a very sophisticated controller. But the point is that to be able to design the controller, you need to know the model of the aircraft when it is flying. Do you see the complexity of the situation? So, there are various ways of solving this problem, and so what people do is that they have first flown it in very restrictive conditions, using, in fact there are aircrafts which can be made to behave like another aircraft. People have companies with aircrafts, for example, a very fast aircraft, something like an F-16 can be made to behave like a slower aircraft just by control. So, using such methods, you first somehow get the model of an LCA in a very restrictive flight condition and somehow construct a controller. Then with that controller, fly the LCA in some restrictive conditions. Then you get more data, because to be able to get the model, to be able to estimate the model, you need data. You won't get data unless you fly it. Okay, so in fact, this exercise is still going on. As they are able to fly the craft, then they are gradually now getting speed, increasing speed, coming almost towards 1 Mach, and getting more data, and then refining their models and then refining their controller so that they can fly it in more. So this thing goes on. So this itself is a cycle which every control designer has to go through, especially for stable processes or very simple processes in which you can analytically design a model. This is not a problem, but for most complex plants, this is a big problem. So we are going to ask such questions in the rest of the course, and try to get, and we are also going to we are not only going to ask the questions, that is, we are not only looking for solutions to these questions, we are also looking for good solutions to these questions, not just solutions. So whenever we'll produce a quantity, some quantity, we will have to examine how good that quantity is in a given sense, and then maybe optimize and get an algorithm which gives the best such quantity. Okay, and all. So this is what we are going to do in the rest of the course, and we will start with input output things. So we will basically start with filtering, so statistical signal processing, and then gradually move towards state estimation, and then finally go to system identification and some other problems. Thank you very much.